Hi again, everyone. And as promised, we're going to carry on with Gibbs Energy and specifically thinking about the work that we can get out of a system and how Gibbs Energy is going to let us calculate that amount of work. So, one of the ways that we can think about Gibbs Energy is just as the maximum theoretical amount of work that we could get out of a system if all of the energy was being used as work and none of it was going into just waste heat. So right away you can see that that's not a practical or realistic thing that we can get out of it. It's really a what if scenario. If we do something that maximally pulls the work out of it. Or the same thing. So this would be in the case of like a negative delta G, we could get the maximum work out of it done by a system, right? If delta G is negative or delta G is below zero. If delta G is positive, that means we're looking at a non-spontaneous reaction. So something that we're going to have to do something to in order for it to happen. So this tells us that if it's a positive delta G, it's the least amount of energy or work that we'll have to do to the system to get it to work. Of course, we'll need to put in more energy than that to actually get it to work out, because again, some of that energy is going to be spoiled as just friction waste heat. So, like I've said before, it's just the cost of doing business in a real universe that for any real process, we can't get this idealized reversible energy out of it. Okay, so this is the maximum work that a system can do. Actual work is always going to be a little bit more path dependent, even though delta G itself isn't. So if we think about, say, expanding a gas, so this is going to be, imagine if let's say we have a cylinder and there's a piston inside it, okay, and this has a certain amount of weight on top. And again, we're just going to heat up the gas in there a small amount, and it's going to be so incrementally slow that the amount of work that we're getting is exactly equal to the heat that we're putting into the system. So, or the work that, I guess these signs should be opposite. So, the work that's going, silly. The work that the system is doing is exactly matching the heat that it's bringing in. So this would be kind of, again, that idea of maximum amount of work. So this would be, again, a reversible system ideal. A car engine, of course, you're getting work out of the system. You are performing the combustion of gasoline, and it's going to also be a cylinder. So the combustion inside that cylinder area is driving that piston up, and it's also generating a lot of heat, right? So your balance between work and heat is going to be quite a lot less. So even though we can calculate the delta G of combustion, say for octane or for the whatever blend it might be in your gasoline, that delta G is going to be, let's say the absolute value of that delta G is going to be greater than the work that you can get out of that system, only because a certain amount of it is just going to go to waste friction heat. Okay. Good. So we have temperature in one of the terms. So how are we going to account for that effective temperature on Gibbs energy? So if we look at delta G equals enthalpy minus T delta S. I'll also pronounce that tedious just because it helps you remember, because studying thermodynamics can at times be a little bit tedious. We were interested in what this term is doing. So how is it going to affect the overall outcome of the change in Gibbs energy if we change that temperature that the reaction's happening at, up or down? And it's really going to depend on the reaction itself. What's happening with the enthalpy and what's happening with the entropy. So let's make a little chart. So we're going to say the enthalpy, the entropy. Let's look at this term by itself then. So entropy, but then also the full negative temperature times the change in entropy, and then see what effect that has on delta G in the end. So if let's start with an enthalpy being negative. So that means that it's going to release heat from the system into the surroundings. And the entropy of the system is going up. So the energy that's remaining in the system is going to be more diffuse. If you like, it's going to be more scattered. Probably you're going to be producing some gases with some more degrees of freedom for the remaining molecules there. Okay, so if we have the negative temperature, again, in Kelvin, we can't go negative. So this, if we have negative times a positive, it's going to be negative. So a negative and another negative, these are these two terms. So say enthalpy plus negative TDS. Delta G has to also be negative, and so it's always spontaneous. There's nothing we could do to that temperature, to this term, to make it anything but spontaneous. And we can look at this the opposite way too. So if the change in enthalpy is positive, so that the system is bringing in energy, and the system's entropy is going to go down, so it's going to concentrate energy or have fewer microstates or fewer degrees of freedom, or again, kind of like a ham-handed way of thinking about it, but fewer moles of gas, then the negative temperature times the entropy will be positive. And so you'll have a positive and another positive as your two terms. So Gibbs has to also be positive. And there's nothing, again, that we could do to that temperature term, whether it goes up or down, that will make it change. So this is always going to be non-spontaneous. The interesting parts are where we get situations where the sign of the enthalpy and the sign of the entropy are different, right? So if we say that, let's keep enthalpy is still going to be positive, so it's still going to take in energy from the surroundings. This is an endothermic reaction. And entropy is also positive. So even though we're taking energy in from the surroundings, the system itself is going to end up with that energy being more diffuse than it was before. So that makes the negative temperature times the change in entropy negative. And so now we have this positive and a negative, and it is going to determine or be determined, sorry, the spontaneity of the entire process, or the sign of delta G, is going to be determined by the size of that temperature. So in this case, delta G is going to be negative at high temperatures, where this term can overpower the positive effect of the enthalpy. So as long as this term, this negative temperature times the entropy, is a larger in magnitude than the enthalpy term, then it's still going to produce a negative delta G. If that temperature is below whatever critical temperature that's going to happen at, it means we have a positive delta G overall, and this will be at lower temperatures. And we'll be able to calculate, of course, exactly what temperature that changes at. And we can look at the opposite way too. So if the system is going to be releasing a large amount or an amount of heat, but it's also going to go down in the entropy of the system, that means that that negative temperature times the entropy change in the system is going to be positive. And again, we have this balancing terms. So, but the effect is going to be opposite. So now we want, if this temperature term is very high, that means that the positive term here is going to overpower the negative term, and delta G overall is going to be above zero at high temperatures. So this is a case where something could be spontaneous at low temperature, But then as the temperature rises, as the ambient temperature rises, it loses its spontaneity. There will be some point at which we reach equilibrium, and then above that temperature, it's no longer a spontaneous reaction. So let's look at an example of how temperature can change a reaction and see if we can determine the temperature at which a reaction becomes spontaneous. So here we have at 25 degrees Celsius, reduction of copper 1 oxide to copper is non-spontaneous. Okay, so already we're saying that that at room temperature, this is not a spontaneous reaction. So reduction of copper oxide to copper is non-spontaneous, which is another way of saying that copper oxidation at this temperature is a spontaneous process, which again I think should be a little bit more obvious that say this is oxidation is in copper in this sense is the equivalent of like iron rusting, and where we get that patina on the roofs of RMC and some other buildings around Kingston, that green roof is just the spontaneous oxidation of copper into copper oxide. Okay, so let's look at what temperature the reverse reaction becomes spontaneous. So what else do we need to know here? Do we need to know? Yes, we probably do. That the delta S of the reaction is 165 joules per mole Kelvin. We have here 8.9 kilojoules per mole Kelvin, or per mole, is equal to delta H minus 298. So this temperature we get from the question at 165 joules per mole Kelvin, which I just gave you. Okay, we're going to have to know one of these two things in order to calculate it all out. So count on there being at least enough information to solve the question. Okay, so if we want to calculate then delta H, that we can use it. We just do a little bit of algebra and we end up with 58,070 joules per mole. And okay, so what are we talking about at where it becomes spontaneous? So we're going to say that it's non-spontaneous at a certain temperature. So if we're looking at this as a chart, and this is delta G at 0, and we want to say, okay, below 0 or above 0, and this is going to be temperature on our chart. Here at 25 degrees Celsius, it is at 8.9 kilojoules, right? So it's above 0, but we're going to say that it's going down and that at some temperature that's higher than 25 degrees, it's going to cross that line. It's going to be at equilibrium, and then it's going to go below equilibrium and become spontaneous. So we are interested in exactly that temperature. But what we do know is that delta G at that point is equal to 0. The point where it goes from above 0 to below 0 is, well, it's at 0. So we want to say 0 equals delta H minus T delta S. So delta H equals T delta S, or we can write this, since we're interested in the temperature, as delta H per change in entropy at equilibrium. Okay, and we know these quantities already, so we can just fill that in, that this is 58,070 joules per mole over 165 joules per mole Kelvin. And there's our Kelvin because we wanted that to show up again for our units. And this works out to 352 Kelvin. So that's the point at which it becomes spontaneous. So this temperature now is 352 Kelvin. And so we can say it's spontaneous at that temperature and every higher temperature as well, according to this theory anyways. Okay, and so that's it for this one. We're going to carry on next time showing a a more thorough examination of what it means for Gibbs energy at equilibrium and how we can start to relate that to things that we've already seen about equilibrium when we think about kinetics and rate laws. Okay, so I look forward to talking to you then. Thank you as always for watching.